Hi, I am Sanjay Patel. Today we are going to prove some theorems on limit of functions. So this is our first lecture on theorems of limit of functions. So let us start with some basic result. The first result, it says suppose limit x tends to a, f of x is equal to L exists, and the value of the limit, that is the number L, is positive. Okay, then prove that there exists some delta greater than 0 such that fx is greater than 0 for every x belongs to n star of a comma delta. This means in words that the function remains positive on some deleted neighborhood. That is, fx is positive in some deleted neighborhood, of the point A. So let us prove this. Simple meaning of this result is, if a limit of a function is positive, then the function is also positive in some small region around that point at which we are having the limit. So here we are given that limit of fx is L and L is positive. Since limit of fx is L, for every epsilon greater than 0, we can find some delta greater than 0 such that epsilon delta condition will be satisfied. So since limit x tends to a, f of x is equal to L exists, okay, for epsilon is equal to L by 2. See, L is positive, so L by 2 is also positive. You know that L is positive. So for epsilon is equal to L by 2 greater than 0, there exists some number delta such that whenever 0 less than mod of x minus a less than delta implies mod of fx minus L is less than epsilon, that is L by 2. The meaning of this left hand side of this implication sign is x belongs to n star of a comma delta. So whenever x belongs to n star of a comma delta, this implies, now this I want to write in the inequality form by removing this modulus. So I can write this as L minus L by 2 less than fx less than L plus L by 2, and that is nothing but L by 2 less than fx less than 3L by 2. L plus L by 2 is 3L by 2. So what we have proved actually? We have proved that the value of the function fx is always greater than L by 2. It is always greater than L by 2 for every x in n star of a comma delta. Okay, and since L is positive, L by 2 is also positive, so our aim is proved. So thus fx is greater than L by 2, which is greater than 0 for every x belongs to n star of a comma delta. So hence the result is proved. Okay, so it is a very basic and simple result. If a function limit is positive, function is also positive in a small deleted neighborhood or punctured neighborhood of the point A. Okay, let us derive something like the reverse of this. Suppose we have limit of fx is equal to L exist, and suppose we know function is positive, then what can we say about the limit? So something like converse of this theorem. So let me write as a next theorem. Say theorem number 2. It says if limit x tends to a, f of x is equal to L exist, and the function is positive for every x in the domain, and fx is say greater than 0 for every x belongs to domain of f, then prove that the limit L is always greater than or equal to 0. It may be 0 also, not necessarily positive only. Remember that even though the function is positive, limit can be 0. Okay, so let us prove this. This I want to prove by a contradiction, by assuming that what is to be proved is not true. Say we want to prove that L is greater than or equal to 0 here. So suppose if possible, L is less than 0. Suppose if possible L is less than 0. So that implies minus L is positive. That implies minus L is positive. Now we are given that limit of fx is L. So for every epsilon we can find delta, so that epsilon delta condition of the definition is satisfied. So what I want to do here is, let us take epsilon is equal to minus L by 2. This number minus L divided by 2, and we know it is positive because minus L is positive, so minus L by 2 is also positive. Then as limit of fx as x tends to a is equal to L, for this epsilon I can find some delta such that whenever 0 less than mod of x minus a less than delta is true, we have mod of fx minus L is less than this epsilon, which is equal to minus L by 2. Again we will open this modulus and write in this inequality form. So this can be written as, this implies L minus L by 2. Let me write like this more precisely: L minus L by 2 less than fx less than L plus minus L by 2. Okay, like this. What is the meaning of this thing? That is 3L by 2 here, because minus plus, so L plus L by 2 is 3L by 2 less than fx, and less than L minus L by 2 is L by 2. Okay, so what I have proved is this: okay, fx is less than L by 2 for every x belongs to n star of a comma delta, because 0 less than x mod of x minus less than delta means x belongs to n star of a comma delta. So whenever x belongs to n star of a comma delta, fx is less than L by 2. I want only this much. Here a less than b less than c, everything is true. So this is also true, b less than c is also true. But we know L by 2 is negative because L is negative. Okay, because L is negative. So what I have proved? That is, we have proved that fx is negative for every x belongs to n star of a comma delta. And this is a contradiction because we are given that in the hypothesis fx is always positive for all x in the domain. So this is a contradiction. This is a contradiction to the hypothesis that fx is positive for every x belongs to its domain. For every x belongs to df means domain of f. Okay. Therefore, our supposition must be wrong. So, our supposition must be wrong. What was our supposition? Remember, we have started with this fact, with the assumption, that L is negative. So this is wrong. L less than 0 is wrong. So what is true? If L is not less than 0, L is greater than or equal to 0. So that implies, it follows that L is greater than or equal to 0 is proved. So remember, if a function is positive for every x, then the limit of the function, if it exists, is always non-negative. And using this result, we can derive one very useful and interesting corollary. Say, let us write as a corollary or a consequence of this theorem number 2. It says if fx and gx are two functions, if f and g are two functions from x to r such that fx is less than or equal to gx, for every x belongs to x, okay. Then prove that limit of fx as x tends to a is less than or equal to limit of gx as x tends to a, provided this limit exists. Let me write, provided both the limits under consideration here exist. Means if this limit of fx and limit of gx both exist, and if we have this inequality or relation between the two functions values, then limit also follow the same rule or follow the same inequality. The proof is very simple. It follows from this our previous theorem. Remember, the previous theorem is this, that if limit of x exists and fx is positive, then the limit is also non-negative or greater than or equal to 0. So using this result, theorem number 2, I will be proving this simple corollary or a consequence of this result. So the proof of this goes like, f and g are two functions with this relation. So let me define a function, new function, say capital F, from x to r as capital F of x is equal to gx minus fx for every x belongs to capital X. So from the hypothesis, as fx is always less than or equal to gx, as fx is less than or equal to gx for every x, we have gx minus fx is non-negative for every x, and that means the function capital Fx, because capital Fx is gx minus fx, is always greater than or equal to 0 for every x belongs to the domain. Okay. So function is this, and since limit of gx and limit of fx both exist, limit of fx also exists. Okay. So I can say by hypothesis, limit as x tends to a, capital F of x exists. Also, by hypothesis, limit x tends to a, capital Fx, okay, that also exists. Limit x tends to a, gx minus fx, okay, which is nothing but this thing. So fx is non-negative. Remember, fx is non-negative, and limit of this fx, this exists. This thing exists. Okay, because both of this limit of gx and limit of fx exist. So limit gx minus fx exists. That is limit of fx exists. Okay, so whatever the this limit is, that limit is also what you can say is limit is always greater than or equal to 0. So this limit is always greater than or equal to 0. Okay, so what we are proving here is that is this value is greater than or equal to 0, means limit x tends to a, gx minus limit x tends to a, f of x is greater than or equal to 0, because if fx is greater than or equal to 0, then limit of fx is also greater than 0 if it exists. Okay, so this proves the required result. Just taking this term on the right hand side, we can rewrite this as limit x tends to a fx is less than or equal to limit x tends to a g of x. Okay, taking this term on this side and writing in the reverse order, we'll get the required result. So hence the result is proved. Hence the result is proved. Okay, fine. Now next I am going to prove a very famous result known as sandwich theorem for limit of functions. In the sequence limit of sequences, we have proved the same kind of result, sandwich theorem, for limit of sequences. So our third theorem is the sandwich theorem, which is called sandwich theorem. So it is an important theorem. So in this case, we have three functions, fx, gx and hx, and we have some relation between the values of these three functions. Then we can conclude what happens to the value of the third function. Let me write the statement like this. Let f, g and h be three functions, okay, be given functions with the property that fx, or let me write this way, fx, sorry, f of x is less than or equal to g of x is less than or equal to h of x for every x belongs to capital X. So we have this relation between the values of these three functions. And also in this case, what I want to prove is this: if limit x tends to a, f of x is equal to L is equal to limit x tends to a, h of x. Remember, the limit of the first function here and the third function in this inequality, they are both are equal and both exist. If this exists, okay, then prove that the limit of the middle function, as this limit of f(x) is L, limit of hx is also L, the limit of the middle function gx will also be equal to L. So prove that limit of gx as x tends to a also exists and is equal to L. Okay, this also exists. And note one thing, I cannot use the corollary what we have proved in the previous result. Just let me make it clear, because you might be thinking that it is just an application of the previous corollary. See, in this corollary, where fx is less than or equal to gx, then we can apply limit on both the sides, limit of fx less than or equal to limit of gx as x tends to a. But that we can apply only if both the limit exist. Here we are not, okay, both the limit exist. Okay, so here I cannot write directly fx less than or equal to gx implies limit of fx less than or equal to limit of gx, because we don't know about the limit of gx. Limit of gx may or may not exist. It is not given. No information is given about the limit of the function gx. Okay, so let us prove it independently. Remember, it is not it cannot be derived from the corollary. So let us prove. It is very interesting and very simple theorem. Note that limit of fx and limit of hx both exist and is equal to L. And I want to prove that limit of gx exists is equal to L. So let us start with an epsilon greater than 0 be given. Okay. So first step, as limit x tends to a, f of x is equal to L, there exists some delta which I want to call delta 1 greater than 0, such that whenever 0 less than mod of x minus a less than delta 1 implies mod of fx minus L is less than epsilon. Okay, this I can write as L minus epsilon less than fx less than L plus epsilon. Let us call this as result number 1. The same way, let us use the second limit of hx. So again, as limit as x tends to a, g of x is also L. For the same epsilon, I can find another delta. Let me call it say delta 2. There exists some delta 2 greater than 0, such that whenever 0 less than mod of x minus a less than delta 2, so whenever 0 less than mod of x minus a less than delta 2 implies mod of gx, sorry, not gx, here this function is hx, it is my mistake here. Now gx is the middle function, and the third function limit is also L, so it must be hx here. So limit of hx is L, so there is some delta 2 such that this condition is epsilon delta condition is satisfied, and this we can rewrite as above as L minus epsilon less than hx less than L plus epsilon. And let me call this as result number 2. I want that 1 and 2 both holds for all x, for all common x. So I must put the common value of or minimum value of delta 1 and delta 2. So let us consider delta is equal to minimum of delta 1 and delta 2. Now what happens here is, we know as delta is positive and this means two things: delta is positive and also delta is less than or equal to delta 1 and delta is also less than or equal to delta 2. Okay, so therefore if I choose 0 less than mod of x minus a less than delta, remember that it is less than delta 1 as well as less than delta 2. So both result 1 and 2 holds true for such x. Okay, any x satisfying this condition, result 1 and 2 both are true because it satisfies these two conditions. So I can write, if this is true, then by result 1 we have L minus epsilon less than fx less than L plus epsilon is true, and L minus epsilon less than hx less than L plus epsilon is also true because of 1 and 2. Okay, so what I can write, remember this is true as well as this is also true. So I want to rewrite as L minus epsilon less than fx. Okay, and hx is less than L plus epsilon. See, a less than b less than c is true, so a less than b is true. Similarly, p less than q less than r is true, so q less than r is also. So I am taking this part from this second inequality and this part from the first inequality. But we know what is the relation between fx, gx and hx. So I can write this way. This implies L minus epsilon less than fx less than or equal to g of x less than or equal to h of x and less than L plus epsilon. This is given because we have f less than g less than h, that is given in the hypothesis. So here everything is true, all this inequality holds for all x satisfying this condition, for all x satisfying this condition. So what is the conclusion here is I can take the terms in this inequality whatever I want. So what I will do is I will take this and this, because a less than b less than c less than d less than e, everything is true. So I can take a less than this, a less than this. So therefore 0 less than mod of x minus a less than delta implies, what I can write is L minus epsilon less than g of x less than L plus epsilon, and that means mod of gx minus L less than epsilon. So what is the meaning of this? We have started with an epsilon greater than 0 and we have found a delta satisfying this condition, and it means that limit of gx exists and is also equal to L. So thus the conclusion is, thus limit x tends to a, g of x is equal to L is proved. This is proved. Okay, so very useful result. Whenever we have a relation between some three functions, say something less than or equal to something less than or equal to something, okay, and we know that the limits of the first and the last term exist and both are same, then the limit of this middle function will be sandwiched between the two limits and it is equal to the same limit, same value. Suppose this limit is 3 and this limit is also 3 as x tends to a, then limit of this function is also 3. So this we can use to prove some interesting examples. Okay, so these are the important results. In the next lecture, we are going to prove some more results about limit of functions, and one very important relationship between the limit of functions and limit of sequence we are going to establish. Okay, so thank you.